Hello everyone, and welcome to the Big O notation lecture in this section of the course. In this lecture, what we're going to be doing is just going over the corresponding Jupyter notebook that accompanies this lecture. We won't be doing that much or really any live coding. We'll just be discussing the functions that we previously looked at. Okay, with that being said, let's go ahead and jump to the Jupyter notebook. Alright, this is the Big O notation notebook. And I recommend that you actually read through this notebook, and then if anything doesn't make sense to you, come back to this video lecture, where we're going to be going over it. Alright, so we previously discussed these two functions. And now remember, these functions take in an n, and then they return the sum of the numbers from 0 to n. The first one did it iteratively, and then the second one took this algorithm, this n times n plus 1 divided by 2. So what we want to do is develop some sort of notation to objectively compare the efficiency of these two algorithms. And a good place to start would be to compare the number of assignments or operations each algorithm makes. So let's start with just assignments in general. So if we look here, the original sum1 function will create an assignment n plus 1 times. And we can see this from that xrange or range-based functions. Just a quick note, since this is in Python 2, we're using xrange, which is just a generator, but range in Python 3 is the same. So don't worry about that detail, we're really just discussing Big O notation here. So continuing on, this original function will create that assignment n plus 1 times. So this means it will assign that final underscore sum variable, this one right here, it's going to assign it n plus 1 times. So here is the 0, and then it assigns it n plus 1 times. So we can say that for a problem of n size, here it's input, this function will take that 1 plus n steps, or that n plus 1 steps. And this n notation right here allows us to compare solutions and algorithms relative to the size of the problem. So since sum1, this first function of 10 will be different than sum1 of, let's say, 1,000,000, if n equals 10 or n equals 1,000,000, they could take very different run times. But if we get some sort of Big O notation that's relative or in terms of the input, we can objectively measure it across any sort of input as long as the Big O notation is relative to the input. So that's where this n is going to come into play. And we'll see that when we actually formalize the notation. Okay, so let's go ahead and scroll down here and zoom in a bit so we can discuss the formality of Big N, or Big O notation, excuse me. So Big O notation, formally we can say it describes how quickly runtime will grow relative to the input as the input gets arbitrarily large. So there's 3 points there. Let's go ahead and examine them more closely. So first point, this first bullet, we want to compare how quickly runtime will grow, not compare exact runtimes, since those can vary depending on the hardware. So as we mentioned before, we want to compare objectively these two algorithms, not based on runtime. And what I mean by not based on runtime is not based on exact runtime. We just want to compare how quickly runtime will grow. So I don't want to compare, let's say, 10 seconds versus 12 seconds. I want to compare something objectively, and that can be how quickly runtime will grow. Second point we want to make is, since we want to compare the variety of input sizes, we're only concerned with runtime growth relative to input. And that's going to be where this n notation comes into play. And then the third point is, as n gets arbitrarily large, we only worry about terms that will grow the fastest as n gets large. And to this point, we can think of Big O analysis as sometimes also known as asymptotic analysis. Okay, so let's go ahead and scroll down to the table where we can see how this syntax works. So the syntax for that first function can be said to be Big O of n, since its runtime grows linearly with the input size. In this next lecture, we'll go over more specific examples of these big O types and types, but just to note, this is what the format of the big O notation is going to look like. It's going to have a big O and then the big O notation or performance inside the parentheses. So here are some common runtimes of big O functions. So the common ones are constant, logarithmic, linear, log linear, quadratic, cubic, and exponential. So what I'm going to do now is use a library called matplotlib to plot out the differences between these big O's. So you can go ahead and check out that code yourself, but don't worry about it. We're just discussing big O notation here, not matplotlib. But I use that code to create this plot here. So here we can compare the growth on relative runtime versus the size of the input. So you can see here in constant time, you'd have a straight line, and then you'd also have logarithmic, log linear, quadratic, and cubic and exponential. So let's go ahead and zoom out a bit so we can see them all. Here we go. So you can see that there's a big impact if you don't have a good big O for your algorithm. So there's a huge difference that a big O efficiency can make for the same n value against some sort of projected runtime. And clearly we want to choose algorithms that stay away from any exponential, quadratic, or cubic behavior, these guys, since they grow so fast. You can note that for small input sizes, so very low values of n, they're all very similar and to each other. So if you only expect to deal with low n, for certain cases, the big O doesn't actually matter to you. But as you can see, as n grows larger, you'll get huge differences depending on the efficiency of your algorithm. So in the next lecture, what we're going to do is learn how to properly denote this big O, and then we'll look at examples of various problems and calculate the big O of them. So what did we see in this lecture? We just saw a quick, kind of almost a preview of the various big O types, why it's so important to choose or try to create an algorithm that has an efficient big O relative to its performance and runtime. Okay, so in the next lecture, we're going to see a bunch of examples and break down their big O. All right, thanks, and I'll see you at the next lecture.